under gravity. And what I want to do in it is to address a common misconception about using positive and negative values of g, the acceleration due to gravity. What we've got here is a stone, and it's thrown upwards from horizontal ground with a speed of 14.7 meters per second. And assuming that there's no air resistance and taking g to be 9.8 meters per second, find in part A the time taken to reach the ground again. In other words, the time of flight. And then in part B, the maximum height reached. Now when you're doing questions like this, I would strongly encourage you to draw a diagram. And this would be a typical kind of diagram where you've got your particle here being projected from the ground upwards at a speed of 14.7 meters per second. Now, I would want to put on this diagram the acceleration due to gravity, which acts vertically downwards. So if we mark that in here with a double arrow, okay, it's going to have a magnitude of 9.8 meters per second. Now, when the particle goes up vertically, it comes to instantaneous rest at the top here. So at the top here, v would be equal to 0. I'll just put an arrow here showing that it's come to instantaneous rest, and we'll just put here 0 meters per second. Okay? And when it comes down again, when it reaches this same level that it was projected with, it's going to actually be travelling at the same speed as it was originally projected at, but only in the opposite direction. Quite often people ask me, why hasn't it come to rest? Okay, why isn't it 0 when it hits the ground? Well, we're looking at the instant just before it hits the ground. Now, when it comes to working out the time taken to reach the ground again, the time of flight, we're looking then for the time it takes to go from here all the way up and then back down again. And I can do this in several ways. And I'm going to show you the different ways that we can do this. The way that I prefer though is this one. It's got lots of advantages where we look at the total flight in one go. Okay, let's just put this up here, the total flight, as a subtitle. Now when you're doing any of these questions, because we're dealing with vector quantities, we need to associate a positive sense. And normally it's good practice to take the initial velocity and take the positive sense in the direction of initial projection. So this was initially projected upwards, so I'm going to take upwards as being positive. Okay? It will still work if you do this problem with the positive sense downwards, but it's not good practice. Okay? Now what I'm going to do next is to look at a Suvat based equation. So remember, S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. Now for the displacement S, when the particle starts here, it gains a displacement, a positive displacement, and then it loses it. Okay, when it comes back to here, it might have travelled quite a bit of distance, but its displacement is 0. It's back where it started. As for u, the initial velocity, that's going to be positive 14.7 because it's in the upward sense. I'll leave off the units because I haven't got much room to do this, okay, and it'll just give me a bit more space. V, the final velocity, well that's going to have a magnitude of 14.7, but it's in the opposite sense to what we've got here. So it's going to be minus 14.7. Now for A, the acceleration, well, the acceleration is 9.8 meters per second. It's acting downwards in the opposite sense to what we've got here. So throughout the total flight, we take A to be minus 9.8. And this is the bit that often causes confusion. I find that people ask, why do we keep it as minus when on this stretch on the way down it's moving in the positive sense? Well, it's not, okay? It's still negative compared to this. And I'll show you in a moment, when we've completed this method, the alternative, slower method, where I look at the motion going up and the motion going down in two separate stages, and you'll see it works, okay? This method here. Now we've got to find t, the time of flight, the time taken to go up here and back down here, and I'm going to call that big T, say, okay? So what could I use then? What equation could I use to connect these together to find out what t is? Well, I'm going to look at using the equation s equals ut plus a half at squared. And using that equation, what we're therefore going to have is for s, it's going to be 0 equals u, which is 14.7, multiplied by t. Then it's plus a half at squared. Well, if I half a, that's going to be minus 4.9. So what I'll do is I'll put that in brackets, minus 4.9, and we multiply that with t squared. So that's going to be big T all squared. And what I can do next is just factorize this equation. I can pull out t as a common factor. So we've got t multiplied with 14.7 and then minus 4.9t. And because this is factorized, we can therefore have each factor equaling 0. So I could say that this t here would equal 0, or the factor here would equal 0. That is 14.7 minus 4.9 t, that could equal 0. Well, when s was equal to 0, that is the displacement was equal to 0, then clearly the time would be 0. But that's not of interest to us. It's this value of t that we'll be interested in. And so therefore, if I rearrange this equation, it will give me the time of flight. Okay, the time of flight, which is given by t, equals, well, it's going to be 14.7 divided by 4.9. And that comes out very nicely at 3 seconds then, okay? 3 seconds is that time of flight. Now this is the method then that I prefer doing when it comes to questions like this. But the other method, I'll call it the slow method if you like, okay? Let's just put it here. Slow method considers the motion in two parts, going up and then coming back down again. And so I'll take you through this and you can see how I work with G in this particular method, okay? So if we start with going up, okay, looking at the upward motion, then I'm going to take upwards as positive because that's the initial projection, okay? So we'll take upwards as positive. I'll set up my SUVAT based equation. We've got S then, U, V, A and T. And with this, what is S going to be? Well, I don't really know what S is going to be. That'll be that maximum height there. So we'll leave that blank. When it comes to U, that's going to be 14.7. It's in the positive sense. Now V, the final velocity on the way up, well, that's going to be 0. It's going to come to instantaneous rest. So we'll put that as 0. The acceleration due to gravity, well, that acts downwards as we go up. And so it's going to be minus 9.8. And I'm going to want to work out what that time is to go from here up to the maximum height. I'll call that, say, T1. Okay? T1. So what equation would we use then to bind these quantities together and get t? Well, I want one that doesn't include s. So that's going to be using, let's say, v equals u plus at. v equals u plus at. And if I rearrange this for t, we therefore get that t equals v minus u all divided by a. And substituting my values in, for t, I've got t1, and then it's going to equal v, which is 0, minus u, which is minus 14.7, and I divide that by the acceleration due to gravity, which is minus 9.8. So I end up with a negative value over a negative value, giving me a positive value for t1. So t1, the time to go up, turns out to be 1.5 seconds. Now, I could double this value here because it's a symmetrical problem, and you'll see that I get 3 seconds if I double the 1.5, which agrees with the time of flight. But that's not the point behind this. I want to just show you how I would handle the next stage coming down, okay? If I was to look at going down, let's just put it here, going down. Again, I need to set up a positive sense, but going down, I'm starting from the top here, and it's initially at rest. So I'm going to take downwards as positive. Okay, so we'll go down as positive for this stretch, and setting up my Suvat based equation, let's put this up again, S, U, V, A and T. Then S will be this displacement down here. I don't know what it is, so I'll just leave it blank. U, well, the initial velocity was 0, okay? V, the final velocity, well, that's 14.7. It's in the positive sense, so that's 14.7. And now when it comes to acceleration due to gravity, that is going to be positive 9.8. So I'll put that down as positive 9.8. It's going in that positive sense. T, well, we'll call this T, T2. It should turn out to be 1.5, but I'm just doing this to prove a point, okay? And again, what I would want to do is use v equals u plus at. So let's just put that down here again, using v equals u plus at. And rearranging it, again, we've got t equals v minus u all divided by a. And substituting the values in, we've therefore got t2, the time it takes to come back down again, equals v, 14.7, minus u, minus 0 in other words, divided by acceleration due to gravity, which this time is positive 9.8. And notice we get a positive value on the top divided by a positive value gives us a positive value. And this turns out to be 1.5 again, 1.5 seconds. So I've split that into two parts, and so therefore the total time of flight is just to add those two times together. So just for completeness, we'll put this in here as therefore the time of flight. Okay, time of flight, well, that's going to be equal to the 1.5 here plus the 1.5 there, which is 3 seconds, and it agrees with what we've got here. But as I say, the point behind doing this was to show you that this method works, okay, when we take a to be minus 9.8. When we look at the value of a when compared to the start, okay, it was in the negative sense, irrespective of this section here when it comes down, okay? Now for the last part, part B, we've got to work out the maximum height reached. I'm going to call that maximum height, we'll just say max height. I'm going to call that maximum height h, okay? Now what I'm going to do is look at the upward projection, okay? So I'm going to take positive as being upwards. And so again, we build a SUVAT based equation. So we're going to have S then, U, V, A and T. And S, well, S is going to be H. It's in the positive sense, okay, so that's going to be H. U is positive 14.7. V, well, that's going to be 0 because it comes to instantaneous rest. And the acceleration, well, that's going to be minus 9.8 because it's in the opposite sense to what we've got as being positive, okay? I could actually put T in at this stage. It's 1.5 if I had worked out, say, this method here, or even with this method, because the symmetry, I know that it's going to be half of the 3 seconds. So I could put that in as 1.5, but you can solve this problem quite easily without knowing the time, just by using a SUVAT based equation that doesn't involve time. And that would be using v squared equals u squared plus 2as, okay? What I'll do though is encourage you to experiment with your equations to check that you can get the same answers as what I get, okay? Try using, say, s equals ut plus a half at squared, or s equals vt minus a half at squared, or even s equals u plus v divided by 2 all times by t. But this is the one that I would prefer to do something like this with. Okay, so rearranging this for s, we therefore get s equals v squared minus u squared all divided by 2a. You might not want to rearrange your equation straight away, okay? You might want to just substitute your numbers in and then rearrange it. Obviously that's up to you. So substituting the values in, for s we've got h, and this equals v squared, so that's going to be 0 squared, minus u squared, so that's going to be 14.7 squared, and that's all divided by 2a, so that'd be 2 multiplied with minus 9.8. And if you work this out, you end up with a positive value for h, as we would expect, and it turns out to be 11.025, and that be measured in meters. Well, I hope that's helped in your understanding of how we do this kind of problem, and this misconception that so many people have over using the acceleration due to gravity, whether it's minus 9.8 or whether we should take it as a positive value. It all depends on the direction that you associate as positive